Hello and welcome to Physics 111 at Dell Tech. My name is Dr. Mark Taylor. This video is one of several videos designed to review specific math skills that will be useful to you in this course. You're probably already familiar with presenting numbers in what we call the decimal format, which, as the name suggests, uses the decimal point to help show you how big or small a number is. This video will introduce you to another format used to display numbers called scientific notation. Scientific notation is a method of displaying numbers using powers of 10, which makes it especially useful for displaying very large or very small numbers. After we cover how to create numbers in scientific notation, we'll practice converting numbers, first from decimal to scientific notation, and then from scientific notation back to decimal format. One of the many key functions of a calculator that makes it a scientific calculator is the ability to use scientific notation format, which leads us to one of the most important parts of this video, how you can input numbers in scientific notation on your own calculator. To do this, you'll need to find two very specific buttons on your calculator. The Enter Exponent button, which allows you to input simple scientific notation values, and the Change Sign button, which allows you to change positive sign numbers to negative sign numbers and vice versa. Unfortunately, every calculator is different, so we'll briefly review the various versions of each of these two buttons so that you can identify the two buttons on your own particular calculator. Before we do some calculations with scientific notation on a calculator, we'll briefly mention the shorthand version that many, but not all, calculators and computer programs use to display numbers in scientific notation. It's slightly different than the way we would do it. And then finally, we'll use scientific notation values in various calculation problems so that you can get used to using your own calculator and interpreting the results that your calculator displays. So scientific notation is a useful method for expressing all real numbers, but it's particularly useful for displaying very large or very small numbers. It's based on powers of 10. So powers of 10 would be 10 to the 1, which is 10, 10 to the 2, 100, 10 to the 3, 1,000, etc. But we can have negative powers of 10 as well. 10 to the negative 1 is 0.1, 10 to the negative 2 is 0.01. And we'll go over that in another slide. But it's based on powers of 10. And the format for standard scientific notation is this: n, some number, times 10 to the x. Now, you just can't have any number be n or any number be x. There are rules. N has to be some number between 1 and just under 10. So it can't get to 2 digits before the decimal place, but it can go from 1 to 9.99999 forever. For example, n can be 1 or 1.0. It can be negative 2.67, 7.003, where you could write it as positive 7.003, negative 9.9992, etc. Any number between 1 and just under 10, positive or negative, can be the n. X is always displayed as an integer power of 10. In other words, a positive or negative whole number. So negative 9, negative 3, 0, plus 2, plus 14, etc. These could all be x. So examples of numbers in standard scientific notation where the n is between 1 and just under 10 are 5 times 10 to the 7, which is the same as 50 million. And we'll get to that in a minute. Negative 3.16 times 10 to the 8. That's actually equal to negative 316 million. 4 times 10 to the minus 12. That's an incredibly small number. That's a number where it's 0 point and then 11 zeros, and the 4 starts in the 12th position after the decimal place. 6.02214076 times 10 to the 23. If you've ever taken chemistry, you might be familiar with this number. It's called Avogadro's number. It is also known as a mole. It's just a giant number that's very convenient to use in chemistry problems. And then the last one, negative 7.99 times 10 to the minus 8. You'll notice there are two negative signs. One is the sign of the whole number, the negative 7 part of that number, and one is the power of 10 is a negative number, negative 8. So the negative 7.99 tells you the whole number is negative, and the 10 to the minus 8 tells you the number is very, very small. So this would be written in decimal as negative 0.7 zeros, and then the 7 starts in the 8th position, so it'd be 799. So it'd be 0.0000, that's 4, 000, that's 7, 799. So note that large numbers bigger than 1, we're going to call those large numbers, they'll have positive exponents. So 6,000 would be represented as 6 times 10 to the positive 3. And we don't usually write the positive when it's positive 3. Small numbers, in other words, numbers less than 1, will have negative exponents of 10. For example, 0.006 is equal to 6 times 10 to the minus 3. And we'll go over how you would determine these. So before we go over actual examples, let's go over our powers of 10. Remember, any number that's raised to the 0 power is 1. So 10 to the 0 is 1. An example of using that in scientific notation would be 6 times 10 to the 0. Well, what that's really saying is 6 times 1. Well, that's just 6. That's what it would be in decimal format, 6 or 6 point. The number 10 is also 10 to the 1 power. So anything raised to the 1 power is just that number by itself. So 9 times 10 to the 1 is another way of saying 9 times 10, which is just 90. 100 is 10 to the 2 power, or 10 squared. So an example of that would be 3.4 times 10 to the 2. Another way to think about that is it's 3.4 times 100, or 3.4 hundreds, or 340. 1,000 is 10 to the 3. You'll notice the number of zeros in each of these is equal to the positive power of 10. So using that, 7.2 times 10 to the 3, that's 7.2 times 1,000, or 7.2 thousands, that's 7,200. 1 million is 10 to the 6. You'll notice there's 6 zeros there. 2.34 times 10 to the 6 is 2.34 million, or 2,340,000. 1 billion, we add 3 more zeros. Now it's 1 with 9 zeros. That's a billion, 10 to the 9. So 6.05 times 10 to the 9 is 6 billion 50 million. Now for numbers less than 1, we have to use powers of 10 less than 0. That is, we have to use negative powers of 10. So again, we start with 10 to the 0 is equal to 1, and we can use that to give us numbers like 7.3, which in standard scientific notation would be 7.3 times 10 to the 0. But if we want to go smaller than 1, we have to use negative powers, as I said. So 10 to the minus 1 is the same thing as 0.1. So 2 times 10 to the minus 1 is the same as saying 2 times 1/10. 2 times 1/10 would be 2/10, or 0.2. 0.01 is 10 to the minus 2 power. So 3 times 10 to the minus 2 power would be 3/100ths, or 0.03. 0.001 would be 10 to the minus 3 power. So 4.32 times 10 to the minus 3 would be 0.00432. One way to think of this is this would be a little more than 4 1,000ths, and you would start writing the 4 in the third position. In fact, let's look at the original powers of 10 written here on the left, these values. You'll notice that if you look at the powers of 10 that they correspond to, each number starts at the position that corresponds to the number after the decimal place. So minus 1 power means the 1 is in the 1 position after the decimal place, literally the minus 1 position. When the power is minus 2, the 1 starts in the 2 position. You can think of it as the minus 2 position. When the power is minus 3, the 1 starts in the quote-unquote minus 3 position. So look at the final scientific notation versions, numbers like these. Where does the 7 appear? It appears in the 0 position, that is, the position before the decimal place happens. When we have a power of 10 that is minus 1, the 2 starts in the quote-unquote negative 1 position, or the first position after the decimal place. When the power is negative 2, the 3 starts in the second position after the decimal place. And when the power is negative 3, the 4 starts in the third position after the decimal place, the quote-unquote negative 3 position. And then you just put all the other digits in there. The 3 and the 2 just follow the 4. So you don't need to worry about where the 3 and the 2 are. All you do is figure out that the 4 is in the third position after the decimal place, and then you just write the rest of the numbers from the coefficient. So if we look at the next examples here, we have 0.000001, and that's 1 millionth. That's a decimal point followed by 5 zeros, not 6, and then the 1 appears in the 6th position after the decimal place. So anytime you see a power of negative 6, you know your digits will start in the 6th position, which means you'll have 5 zeros leading up to it between the decimal place and that first digit from your scientific notation value. So here we have 7.00 times 10 to the minus 6. We basically count until we get to the 6th position, and then we just start writing 7 and then 0, 0. So our answer is 0.00000, that's 5 zeros, 700. 10 to the minus 9 is 1 billionth, so the 1 appears in the 9th position. So it's 0.8 zeros and then a 1. So when we have a scientific notation using a 10 to the minus 9, like 1.302 times 10 to the minus 9, we write 0. And then 8 zeros, and then we start the 1 at the 9th position. So it becomes 0.0000000, that's 8 zeros past the decimal point, 1302. So let's look at creating scientific notation values from decimal values. Pretty easy to create scientific notation format if you start with a decimal format. All you're doing is moving the decimal point from where it used to be to a new position that makes whatever your number is look like it's between 1 and 9.99999. So here we have 500, and you might have the decimal point written, you might not have the decimal point written. You have to write it, remind yourself where it is, and then just start moving it. And you'll notice I have to move it twice to the left to create 5.00. So I have artificially made the number smaller by 2 powers of 10 by moving the decimal point to the left. Well, if I've artificially made the number smaller, I have to fix that by then multiplying that 5.00 times a number that will bring it up by 2 powers of 10. Well, that's just 2 powers of 10. So you're multiplying it 5 times 10 to the 2 power, or 10 squared. So think about what 5 times 10 to the 2 means. It means 5 times 100. 10 to the 2 is 100. 5 times 100, that's 5 hundredths, or 500. So it makes sense. Here's a number, 2.087. Well, in this case, the number already has a decimal place in a position that makes our value appear between 1 and just under 10. It's a number just bigger than 2. So we don't have to multiply it by any power of 10, but since this is scientific notation, we want to multiply it by a power of 10 that doesn't change the number, and 10 to the 0 is just 1. It's a disguised version of 1. So 2.087 times 10 to the 0 is really just saying 2.087 times 1, or 2.087. Now we have a larger number, 98,760, and I placed the decimal point there, but it might not have a decimal point. You put it there, and you move it until the number is between 1 and 9.99999. So move it 1, twice, 3 times, 4 times, and now you have a number that would be 9.876 and maybe a 0 there, depending on how many significant digits you have. And this lecture does not discuss significant digits, so we'll worry about that in another time. But you do have to move the decimal place 4 positions to artificially make it smaller by 4 powers of 10. Well, that means you have to fix it by multiplying by 10 to the positive 4 to bring the size back up. 10 to the 4 is 10,000. So 9.876 is a little more than 9 times 10,000, or more than 90,000. Well, it's 98,760. So that makes sense. All right, what if you have numbers less than 1? Well, now you have to move the decimal place in the opposite direction. You have to move it to the right. So you're artificially making the number bigger, in this case by 1 power of 10. So I've made the number bigger. I changed it from 0.465 to 4.65. I've artificially made it larger, so I have to correct that by multiplying it by a power of 10 that will make it smaller again, and that would be 10 to the minus 1 because we only moved the decimal place 1 position. Another way to think about that is the 4 is in the minus 1 position, so it's 4.65 times 10 to that minus 1 power. An even smaller number, 0.0001306. Well, remember, between the decimal point and the 1, there are 3 zeros, which tells us the 1 starts in the minus 4 position. And we can move the decimal place 4 places, and you can do that at first, but after a while you're going to get tired of doing that. Just count where the 1 is. The 1 is in the 4th position in the negative direction, so therefore we have to multiply it by 10 to the minus 4. So it's 1.306 times 10 to the minus 4. So let's take a look at some practice problems where we're converting numbers from decimal format to scientific notation format. And the first number we have is 9,000. And while you don't see the decimal point, we know there's a decimal point after the last 0. And we need to move that decimal place until the number is less than 10, between 1 and just under 10. So we move it to the left 1, 2, 3 times until the decimal point is right after the 9. So that would leave us with 9 or 9.000, depending on how many significant digits we have. But that's for another lecture. So we have made it artificially smaller by 3 powers of 10. Therefore, we need to correct that by multiplying that 9 times 10 to the positive 3. And our answer is 9 times 10 to the 3. Now, there's a whole nother way of doing this if you prefer. Remember, before when we were talking about negative exponents of 10, and we were counting the -1 position, the -2 position, -3 position on the right side of the decimal point. Well, if we put the decimal point back in and we consider the positions to the left of the decimal point, well, this would be the 0 position, that would be the 1, that would be the 2, and that would be the 3. Now, they're not really called that. They're actually called the ones position, the tens position, the hundreds position, and the thousands position. But if you just count them from 0 upward as you move to the left, you'll notice that since the 9, the first non-zero digit, starts in the 3 position, that would be the power of 10 we're going to use. So it would be 9 times 10 to the 3. So the next number is 0.1. And there are a couple ways to do this. We could just move our decimal point 1 position, and that would make it now a 1 instead of a 0.1. And we've artificially made it larger by 1 power of 10, so we'd have to multiply it by 10 to the -1 to correct that. Or we could notice that that 1 is in the -1 position relative to the decimal point. It's really in the tenths position, but we're just going to call it -1 position. So it'd be 1 times 10 to the -1. Looking at the next number, 0.008. Well, that 8 is in the quote-unquote -3 position, so it's 8 times 10 to the -3. Or we could move the decimal point 3 times, making it larger, but we'd have to correct it by multiplying it by a number to make it smaller again, 10 to the -3. Our next number is 5,700,000. Again, there are 2 ways to do this. We could take the decimal point, which is not shown here, and it would be on the far side of the last 0, and we would move that decimal point to the left 6 times until we created 5.7, a number between 1 and 9.999, etc. You can do that. Notice you moved it 6 places, making it artificially smaller by 6 powers of 10, and then you would have to multiply it back up by positive 6 powers of 10 to get your answer of 5.7 times 10 to the 6. Or you could notice that counting from the decimal point, if we put the decimal point back in and we say the first position after the decimal point is what we're calling the quote-unquote 0 position. It's really the ones position. That's the 0 position, and we just count 0, 1, 2, etc. By the time we get to the 5, that's the 6th position. So that tells us we have to multiply by 6 powers of 10. The next number would be 100,001. And we don't show the decimal point all the time. It's over on the far right, and you would have to move it a total of 1, 2, 3, 4, 5 positions to the left, which means our final number would be 1.00001, because we have to go all the way to the last non-zero digit, times 10 to the 5th, because we moved the decimal place to the left 5 times. The number after that, 0.0005622. Well, the easiest way to do this is notice that the 5 is in the 4th position after the decimal place, which means it's going to be a -4 power of 10. So that's 5.622 times 10 to the -4 power. Likewise, the next number, which is a very small number, 0 point, I'll try to get the right number of zeros here, 0, 0, 0, 0, 0, 0, 0, 0, 0, looks like 9 zeros, and then the 3 is in the 10th position, 7, 7, 0, 0. So that would be 3.77, and we'd have to include those zeros because if they're on the right side in a decimal, on the right side of a decimal, they're trailing zeros, those count as significant digits, and we have to include those. So it'd be 3.7700 times 10 to the minus 10, because the 3 is in the 10th position after the decimal place. There are 9 zeros and then a 3. The next number is 645.6000. Again, we have to consider those 3 zeros as significant. They're trailing zeros past the decimal point, so we would include those. And we have a decimal between the 5 and 6 in this number, and we'd only need to move it 2 positions to the left to make it artificially smaller by 2 powers of 10. So that means we have to correct it by positive 2 powers of 10. So our number would be 6.456 with the 3 zeros, 0, 0, 0, times 10 to the 2. 10 to the 2 means the number is in the hundreds. 10 to the 3, the number would be in the thousands. And looking at the last number, 24.80. Well, this is in the tens. 24.80 is a little more than 20, so we only have to move the decimal place 1 position. That's 10 to the 1. So our number would be 2.480. We include the 0 again, times 10 to the 1. 10 to the 1 is just 10. So this is telling us that it's a little more than 2 times 10, which is what 24.80 is. So that makes sense. All right, let's look at the next type of problem. Now we're converting scientific notation format numbers to decimal format numbers. So you're given a scientific notation, and now we're converting it to decimal. So 4 times 10 to the 3. Well, 10 to the 3 is just 1,000, so this is 4,000. Now, you could do that immediately, or you could write it out the long way, and I know you're not used to doing it, so let's do it the long way. We would have a 4, and we'd have a decimal point after the 4, that this number is times 10 to the 3. We're making it bigger by 3 powers of 10. So we have to make it 1, 2, 3 powers of 10 to put our new decimal place in. Well, we have to fill those positions in with zeros to make it 4,000. The next number is 3 times 10 to the minus 1. Well, 10 to the minus 1 is 1/10. So this is telling us that it's 3/10. And we would just write that in as 0.3. You'll notice the 3 starts in the first position to the right of the decimal point. That is the -1 position that I mentioned before. Next number is 6.5 times 10 to the minus 3. This is telling us the 6 will be in the quote-unquote -3 position. That's 3 positions past the decimal point. So we would write 0.006, and then we just complete the number. The rest of the number is 5. That's it. So 0.0065. 6 is in the 3rd position after the decimal place. 5.26 times 10 to the minus 5. The 5 in the 5.26 will begin in the 5th position after the decimal point. That means you're going to write 4 zeros after the decimal point, and then the 5 will start there, and then you complete the rest of the number, 26. So your number is 0.0000, 4 zeros, 526. The next number to practice is 1.9673 times 10 to the 8. This is a very large number, and one way to determine how big that number is to write out the 1.9673 and move the decimal place a total of 8 times to the right. In other words, we're making the number 1.9673 bigger and bigger. 1, 2, 3, 4, 5, 6, 7, 8. And we have to fill that in with the appropriate number of zeros. And you can see this is a very large number. We now get rid of the decimal point, and we can see that this number is very large. I'll rewrite it with the appropriate number of commas. So it's 196,730,000. Next example is 9.0100 times 10 to the minus 3. Well, the easiest way to do this is to place the 9 in the third position after the decimal point. And you'll notice that we kept the trailing zeros, the 00 at the very end, because those are significant. Now, I'm not going over the rules of why numbers are significant or not. I'm just telling you, in this case, they are significant, so we keep them there. Next number is 4.6700. Again, these are significant. Times 10 to the minus 5. So the easiest way to do this is just to place the 4 in the fifth position after the decimal place and then just continue writing the rest of the digits. So it would be 0.00004 in that fifth position, 6700. The next number is 5.413 times 10 to the 2. And just to remind you, 10 to the 2 is 10 squared, or 100. So this is 5.413 times 100. So it's going to be a little bit more than 500. And in fact, when we take these digits and we move the decimal place to the right 2 times, we end up with the number 541.3. The last example is 7.12 times 10 to the minus 2. And again, the easiest way to do this with numbers that are very small, in other words, less than 1 with negative exponents of 10, is to just place that first digit of the coefficient, 7.12, first digit being 7, place that, in this case, in the second position after the decimal point. So your answer would be 0.0712. Okay, so now that you understand a little bit about what scientific notation is, how to write scientific notation, how to convert decimal to scientific notation format and back and forth, let's talk about how to input scientific notation on your calculator, your own calculator. And scientific notation may be input in slightly different ways depending on which calculator you have. Now remember, in the introduction, I mentioned that you're going to need 2 buttons on your calculator, the Enter Exponent button and the Change Sign button. Well, the Enter Exponent button might be different depending on which calculator you have. And here are 3 versions that I found on different calculators. One is a button that just says capital E, capital E. One is a button that says EXP, and these may be capital or lowercase. And one is a button that says times 10 to the X. Do not mistake this button for other buttons. These are the 3 buttons. Look for one of these 3 on your calculator. That is the Enter Exponent button. This button means times 10 to the power of. It replaces times, it replaces the 10, and you literally just put in the power of 10 after you type this button. Never use any of these buttons for scientific notation. The little e button, that is totally different. The 10 to the x button, and a lot of students use the 10 to the x button thinking they can use it for scientific notation. I will tell you, sometimes it works and sometimes it does not work. So please don't risk it. And then the last button is the power button, the raise to a power button. Don't use any of these 3 buttons. Use one of the Enter Exponent buttons at the top. Your calculator will only have one of those 3. So look for the one that you have. And this is the button that will allow you to actually enter your scientific notation. And we'll get to how to do that in a second. You also need a second button, especially when you're doing negative powers of 10. The second button is called the Change Sign button, And there are even more versions of the change sign button depending on which calculator you have. Here are 4 of the versions I've found on different calculators. It might be a minus sign in parentheses. It might be a plus/minus sign. It might be a plus/minus sign with arrows showing conversion of plus to minus and minus to plus, or it might be CHS for change sign. All of these buttons are used to change the sign of your number. In other words, if it's a positive number, it will change it to a negative. If it's a negative number, it will change it back to a positive. And this works either for powers of 10 or for the whole number itself, depending on when you hit the change sign button. Now, most calculators require you to hit this button after you've typed the number, but there are some other calculators that require you to hit it before the number, and there are a third group of calculators that let you do it either way. You're going to have to experiment with your particular calculator to see which format you have to use the change sign button. All right, but don't ever use the regular minus sign button. This is not meant for change sign. Frequently, if you hit this button in the middle of using scientific notation, you'll get an error message. Don't use the simple subtraction button, the minus button. If it's a minus button without a parentheses, that is not the change sign button. Now, before we go into actually using these 2 buttons to input scientific notation on your particular calculator, it's important to discuss how the calculator displays scientific notation once you've input the number, because not all calculators display it the same way. The newest calculators will display it the way you'd like it to be displayed. So a number like 5.74 times 10 to the minus 8 will actually appear as 5.74 times 10 to the minus 8. But many calculators will actually use a shorthand version to display scientific notation. For example, this particular number will be displayed as 5.74 e, lowercase e, sometimes uppercase e, minus 8. And the e in this case stands for the exponent of 10 is. In other words, the calculator is telling you, oh, the number is 5.74 with a power of 10 of minus 8. In other words, times 10 to the minus 8. If you were actually to use computer programs, they frequently use this format. If you used Excel, this is how scientific notation is written in Excel. If you wanted to write scientific notation number within a cell and have it use that for a calculation. So let's now talk about how to input various versions of this number using your own calculator. Now remember, you're going to have to find your particular enter exponent button and your particular change sign button. I'm going to represent the enter exponent button as EE, and I'm going to represent the change sign button as plus/minus. But on your calculator, you may have different versions of both of these buttons. And we're going to go through different versions of 5.74 times 10 to the 8. Sometimes the 5.74 will be minus, that is, the whole number will be a negative number. Sometimes the power of 10 will be negative value, in this case 8, and sometimes both. Let's talk about how to enter various versions. First number is just the number without any negative signs, 5.74 times 10 to the 8. That's 10 to the positive 8. You would input that as 5.74, and then you'd hit the enter exponent button, and then 8. And that would be it. Next, let's do 5.74 times 10 to the minus 8, or to the negative 8. That would be input as 5.74. EE tells the calculator it's times 10 to the, and then you'd hit 8 and then the change sign button, or on some calculators, the change sign button, and then the 8. Check with your calculator. The easiest way to check is type each one of these, hit the equal sign, and then see how it's displayed on the calculator. Now let's do negative 5.74 times 10 to the 8, the positive 8. That would be input as 5.74, change sign. So you're changing sign of the whole number, and then enter exponent, and then 8. And finally, negative 5.74 times 10 to the negative 8 would be input as 5.74, change sign to change the sign of the 5.74, enter exponent, and then 8, and then change sign, or on your calculator, change sign and then 8. Again, check with your calculator. And that's how you do it. And make sure it displays it properly once you've done that. And now you know how to actually input it on your particular calculator. Okay, now that you know how to input numbers and you know what they mean, using your calculator, go through each of these calculation problems and see if you get the right answer. First problem, 6.7 times 10 to the 3 times 3.02 times 10 to the minus 8. And you can pause the video here. The answer is 1.71234 times 10 to the minus 4. Now, most calculators will not display this number in scientific notation. Why? Because if it can fit in decimal form, it will usually use decimal form to display the numbers. So the decimal form of this number will be 0.0001. Notice the 1 is in the 4th position after the decimal place. 1.71234. If you didn't get the right answer, try it again until you do, so that you are inputting your scientific notation in the correct format. The next problem involves a much larger number, 6.022 times 10 to the 23. And if you've taken chemistry or are taking chemistry, you'll probably recognize that number as Avogadro's number. That's the number of particles in a mole. And this number is multiplied by 9.3401. Pause the video here. And the answer is 5.6251502 times 10 to the 24. Now this is a giant number and will likely not fit on your calculator display in decimal format, so it will almost certainly be shown in scientific notation format. The third problem is a division problem, 5.67 times 10 to the 3 divided by 3.02 times 10 to the minus 8. Pause the video here. And the answer is 1.877 with a lot of other digits times 10 to the 11. If your calculator has a large display, it might show the whole number, which is 187,748,344,370.86. Now, the next two problems are really specific to chemistry classes. This next formula that involves a negative log is the formula for calculating pH from hydrogen ion concentrations. So if the hydrogen ion concentration was 7.92 times 10 to the minus 11 molar, that would be the unit, you would take the log of that and then take the negative version of that, which is actually a positive number, because when you take the log of this number, you get a negative number, and then by changing the sign again, you end up with a positive pH value. Now, different calculators do this differently, and some you have to type the change sign button, then the log button, and then the number. In a lot of older ones, you type the number in first, then the log button, and then the change sign button. But you can play with it and see if you get the right answer. The answer is a pH of 10.10, etc., 127 with a lot of other digits. Typically, you'd round this off to only a few digits. Now, this next equation is an example of the inverse function for calculating pH. So instead of calculating pH from the hydrogen ion concentration, you would take the pH, in this case the pH is 4.23, positive 4.23, and you would take 10 to the minus 4.23. So it's 10 to the negative pH power to get the hydrogen ion concentration. So in this case, you would actually use that 10 to the x button that I told you not to use for scientific notation. This is where you would use it. So it would be 10 to the minus 4.23 power. Some calculators you would type in 4.23, change the sign to minus 4.23, and then hit the 10 to the x button. In other calculators, you hit the 10 to the x button first and insert 4.23 and change the sign before you hit the equal sign to get the answer. So pause the video, and the answer is shown here. 5.888 with a lot of other digits times 10 to the minus 5, and this would be in molar if you're in a chemistry class. And since this number is not incredibly tiny or incredibly large, it would be displayed in decimal format on your calculator as 0.0000, that's 4 zeros followed by 5888, etc. You'll notice the 5 starts in the 5th position after the decimal point. The next problem is an addition problem with two different scientific notation numbers. 5.67 times 10 to the minus 3 plus 8.42 times 10 to the minus 4. Now, if you put them in, you can pause the video, and the answer is 6.512 times 10 to the minus 3. Again, this is easily fit on your calculator in decimal mode, so in all likelihood it will be displayed as 0.006512. And the next two problems involve multiplications and divisions, all with scientific notation values. We have 8.12 times 10 to the minus 3 times negative 6.01 times 10 to the 6, and that is all divided by 6.022 times 10 to the 23, Avogadro's number, and it is also divided by 7.4 times 10 to the minus 8. Now, before you type this in the calculator, I'm going to tell you a lot of students will multiply the top two numbers, which is correct, divide by Avogadro's number, 6.022 times 10 to the 23, and because the 7.4 times 10 to the minus 8 is multiplied by Avogadro's number, they'll type times 7.4 times 10 to the minus 8. No, please do not do this. Remember, every number on the bottom of that dividing line, every number in the denominator is divided individually. You divide by 6.022 times 10 to the 23, and you divide by 7.4 times 10 to the minus 8. Otherwise, you will not get the correct answer. The calculator doesn't know that you're still on the bottom. You have to tell it, oh, this is another number on the bottom. I'm dividing by this number, and I'm dividing by this number. And if there's a third one, you're dividing by that number. Pause the video here. And the answer is negative. Remember, there was a negative number in here. So it's negative 1.09511 with a lot of other digits times 10 to the minus 12. Now, a few calculators will be able to display all of those zeros. So you would have negative 0 point and then 11 zeros, and then that 1 would start in the 12th position after the decimal place. So it would be 1 and then 0.9511, blah, blah, blah. All right. And the last formula is really very specific to physics class. This is actually an example of calculating something called Coulomb's law for determining electrostatic force between two charges. And this example has 8.99 times 10 to the 9, that's actually Coulomb's constant, times the magnitude of two different electric charges. 4.2 times 10 to the minus 10, coulombs is the unit that would be used, times 7.3 times 10 to the minus 9, also in coulombs, You multiply those three numbers, and then you divide by the distance squared. So in this case, the distance is 1.56 times 10 to the minus 3. That would be in meters. And then you square that number before you actually do the division. So make sure you hit the square button for that number, so that number is squared, and then hit the equal sign. Pause the video here, and the answer is 1.1326 with a lot of other digits times 10 to the minus 2. This number can easily fit on most calculator displays in decimal format, so it'll look like 0.011326, etc. Make sure you get this correct. If you can do this, you can pretty much do all of the calculations with scientific notation. And with that, we'll stop here.